been doing some work both ALD related and high temperature CVD related on this rather interesting class of unpronounceable materials.
Mike's nicked my joke because I still can't say that word. There's a word in here which I really struggle with, but we'll go for it. As we all know, graphene basically kicked off the study into 2D materials. Several years ago, the guys up in Manchester have got the Nobel Prize for it. But there's also been interest in other materials as well. And if you look here, graphene's got a hexagonal structure, so has boron nitride. But boron nitride is a typical insulator stroke dielectric. But it's got the same together. But together, these two could actually form something like a high-frequency electrode. But there's major interest in the, and this is where I struggle with the word, the transmission metal chalcogenides. And this is basically because these materials, which molybdisulfide, which most of this talk will be about, are semiconducting materials at the single layer limit, so and direct band gap. So they're obviously very much of interest for the semiconductor market and potentially for the opto as well. Currently, in this space over here, there's around about 500 material sets are being looked at or researched. Some of them we are looking at, and one we like as well is we were talking about superconducting materials before lunch, when we were talking about the quantum, is niobium, which we're also looking at as for a potential superconducting material. And we have seen some ALD results from that, which showing transition temperature around about 13 Kelvin from some researchers down in Jena. So why the interest in these 2D materials? Well, if you look at the ITRA roadmap, which I don't think exists anymore unless it's ITRA 2.0, you can see that slowly but surely we'll be coming down in thickness of materials, gate lengths, and these all have an effect on the material properties and could affect the actual mobility inside the films, where you've got 2D materials, where you've got van der Waals forces, structures, you're actually getting less of this mobility loss. So it's very key in the roadmap towards achieving 7 nanometers and beyond. But there's other film properties that are useful about it as well. So if you look at it, how we make one of these devices, basically most people are actually just looking at 2D FET type structure. And if I just put this up so I can go through them quickly. And what you get is basically you have a substrate. Here it's either can be sapphire silicon dioxide, and we've used aluminium oxide. Sometimes it's doped. Then you grow your CVD of ALD of 2D materials, etch out your channels using potentially ALE. Then you split your metal contacts, then you do an ALD of top dielectrics, and you end up with your device at the end. And that's some examples of some devices there, photodetectors, light emitters, and potentially biosensors. And what I'm going to concentrate really on in this section is about the CVD of and ALD of the 2D materials. I'll touch on the etching. Mike's already touched on that, so I shall probably go through those slides very quickly. But primarily we're going to look at these materials. If you look at how you grow these materials, and I never realized when I was a kid, scribbled on a piece of paper with my pencil, that I was actually making graphene, but I missed out on something all those years ago. But if you look at the scalability and quality, most people in this space are really starting to look at CVD and ALD because it does give you the scalability and with good quality. So we are really focused in this area here. Currently we have 2 systems on the market to work with this. One is a high temperature CVD system, as Mike said in the introduction, which we call a nanofab. And the other member system we use is the FlexL ALD system, which Tom has mentioned earlier. And I'll go through both of these areas. Starting with the CVD system, and starting with graphene, because it's the classical one. It's the first one that everybody has grown. Now, graphene, of course, I don't know if everybody knows, but it's actually grown at around about 1050 degrees C. So very high temperature, shows the best quality. You see very good 2D peak here, and there's a very low D peak at the end here, which is used, the D peak is actually used as a sign of quality. As one of my colleagues asked me, what did D mean? And I said, well, actually, I don't know the answer to that, but I will find out. So, but that's the highest quality material. But because it's deposited at 1050, most people then defoliate it, or exfoliate it, and then put it onto a silicon dioxide layer to actually make a device. And that's not really, if you're in Intel or anywhere, it's not a process you want. So we have started to look at other areas, and classically, you know, we're a plasma company. Surprise, surprise, we've looked at using plasma PCVD for this. And, oh, sorry, let me just go down. And you can see, this is some work we did with Southampton University 3 or 4 years ago. You can see that the fact there's quite high D peaks, a lot of defects, but that doesn't really matter so much if it actually achieves what you want it to achieve. It gives you good functionality and good electrical properties. It's not as good as the graphene you've got. And we have recently started looking at actually doing it by remote plasma. We think this might be due to the actual ion damage from using the PCVD tool. We're actually looking at it in remote plasma, and that's work that's ongoing with I think it's Gunn, isn't it, Mike? Gunn is this. So we've got a system out in a company in a university out in Europe, and we're starting to look at that. And you can see the D peak is smaller, again, increasing the quality of the material. And again, this is getting close to where you could actually use it almost in a CMOS type device. I'm just going to go pop off over hexaboron nitride again, just to show that we can deposit it. Again, it's a thermal process. Typically, it's high temperature, roughly around about 1,000 degrees C. So I really want to talk mainly in this talk about molydisulfide. But again, it's high quality. Again, we've used Raman which is the gold standard for measuring of 2D materials, to actually show that we have got a good quality material over a reasonable area as well of deposition. So molydisulfide, coming on to my notes. Obviously, this is you need a source of hydrogen of sulfur to actually grow this, which is very easy because you get hydrogen sulfide. Obviously, going back again to my youth, it was used in stink bombs, but again, you know, it smells and it's very toxic. But it's very easy to transport because it's a gas. For the molybdenum, you actually need the moly chloride or a metal oxide, which you have to heat to sublime and then actually flow it into the system using argon. Again, the best processes we've seen on this, and I will come back to this a bit later on from some very recent results that we've put into the slideshow, around between the 600 and 900 degrees C, depending on the substrate you're going to deposit on. But you can, by playing with the parameters, get very good material. Again, Raman is used, and Mike alluded to it earlier, that he didn't understand the wave numbers, but where you're looking for here, if you've got a single atomic single layer of molydisulfide, you get a difference between the two peaks of 21, which is here. That's the classical one. So you get somewhere between 21 to 22 wave numbers, is very indicative of the fact that you have got single layer molydisulfide. Above that, 24 is, I believe, is a dual layer, and above that, actually, then it's either triple or quadruple. It doesn't change very much above those sort of numbers. Of course, we have to go and check this out to make sure we've got the monolayer of molydisulfide. And you can do this by the fact that molydisulfide as a single layer has got a very strong photoluminescence capability, which you don't see with dual layer. And if you see here, sorry, I'll go into this one. This is very indicative of a single reported layer of molybdisulfide. Is a 30 eV between here, and also there's a peak around here, which we believe is induced by this trion peak and a neutral excitation separated by 30 eV. But using our asylum brethren who are outside, we also checked it to make sure that we could see very much at step height that it was 0.9 nanometers, which was measured on an AFM from asylum to show that we've got single layer molybdisulfide. Now, the biggest problem, one of the biggest problems we had was looking at the quality of the material that we had deposited. With graphene, you can see there's a defect peak. The D peak gives a very big D peak. But the pristine material, we didn't have a way of knowing what was this done. But there was a study done with ourselves, with the National Physics Laboratory, where they've actually deliberately tried to damage the pristine surface to actually then look at the quality of the material that is deposited, is left behind. And Mike, when he was talking about his ALE etching, was saying that the 227 peak, which is the longitudinal acoustic mode peak, wasn't actually present. But this seems to be present when what this experiment did was actually put a pristine piece of molybdisulfide in and then fire ions at it and deliberately damage it to see what came out of it. And you can see multiple peaks. But this one was the biggest one and the biggest one that characteristic. And what we have evolved is the fact that the ratio between the LAM peak and this peak here, the characteristic peak, as a ratio gives you a good sign of the quality of the material that you're depositing in the system. And if you look down here, and we can look at this as some process parameters we've looked, you can see the fact that substrate has a big effect on it. Aluminum and sapphire typically are not far off being the same material, but obviously more crystalline. But you can get very good material by playing around with the properties. And that's reported in this paper here. Don't have to write it down, but the papers, obviously, the slides will be available for you to read and get that notes off it. Of course, then, what do? You've got to put them together to try and make an active device, put some heterostructures together, which is what we've started to look at, very much so. You could see a graphene and a boron nitride and a moly might make some sort of device. And what we've looked at is depositing graphene, then exfoliating it and putting that onto a silicon oxide carrier wafer, and then putting that back into the process system, and then growing molybdisulfide on top. And you will see that when we've done this, the characteristic peaks are all there for the two materials, and the D peak, which suggests that the graphene was being damaged underneath, is not there at all. So again, it's showing that we can actually start making these devices in our system. Probably not at the right temperatures for where we want to be, obviously for doing the proper device structures, but there's a capability there and ability to do this. Of course, the next thing would be, how do you grow more layers, more different materials on top? And we can, on our system, put up to 3 different, what we would call precursors, pods, which would give different materials. We can put up to 6 if it was required, if you wanted to look at different materials. Oh, is this not working? Ah, sorry, it's jumped. It's supposed to build up layer by layer, but it's jumped right to the end. You could start building up a complete device, some graphene, molybdisulfide, then tungsten selenide on top. Now, selenides causes a bit of a problem because the selenium compounds are very, very toxic. So we have to work out how we actually can then actually get them on site to actually do this work. So if anybody wants to partner with us to do that, we'd be very, very interested. Flexel ALD system. People say, well, why do ALD for 2D materials? Well, it's got capability of depositing very thin films and very controllably. We have heard of people depositing graphene, but we, in in tools, but we don't think it's very good, high quality. But there's some typical routes to doing this. You could put down a very thin layer of molybdenum, 1 second purge, you get amorphous molybdisulfide, then you take it out and you do a polycrystalline material over the post anneal. But that's taking you back up to 900 degrees C, so why just not grow it thermally? So it's not actually giving us really any advantages. Second way is to actually then, tungsten sulfide. You could do a single one layer of tungsten oxide, and then actually do an anneal to replace the oxygen with sulfur. Again, a reasonable way of doing it. Again, you can look at the third route, then expose it to a plasma at the end at 500 degrees C. Again, it's still fairly high temperature. But our collaborators at Eindhoven at ALD 2017 actually presented a paper around doing actual ALD of molybdisulfide, which is crystalline. This is the ALD Flex L tool that they did the work on. And you can see we've got an ALD window of around 100 to 450 degrees C, and we see 2D molybdisulfide crystalline at a greater than 300 degrees C. They reported a very robust ALD process, which is self-limiting, with a high growth per cycle, around about 0.1 nanometers per cycle, with a large temperature window. As I said, crystalline films above 300 degrees C, with very low carbon and oxygen content. Again, because it's ALD, you've got real good control of the monolayer thickness, so you've got very, very uniform material. You do see the characteristic Raman profile showing for a layer 21 wave numbers between the two peaks. You can get tunable morphology. Of course, if you use the bias table, which that current tool does have a bias table in there, you've got another way of actually energizing the surface as well. And the potential applications are nanoelectronics and catalysis. So if I could point you towards their presentation, which was presented by Agnetha, I can't say her name. There's two words in this, Agnetha, is it Agnetha? Ageeth Ball and her team. Those presentations I think will be online in about 3 to 4 weeks' time, so you can actually go and look at the full information. So if we come back to this, to finish off looking at our development processes, we've talked about how we can deposit 2D materials. I will very briefly skip over the slides about how we would etch them, because Mike has already discussed this about some of the materials about doing 2D ALE. But you can see there's ways around that. Well, ALE Mike has done this. But as Mike has rightly pointed out, when we've etched this material, the 227 peak does not appear at all. It's not, so there's very little damage at all. And then the top gate, again, in the ALD tool, you can deposit the aluminum oxide and 2 nanometer aluminium E-beam evaporated to get your direct. No direct tail on graphene, but you can defoliate the graphene and deposit some materials. We don't see any damage to the graphene from using TMA and oxygen. There are gateways around us doing that because we can use the pressure to actually make sure we get low damage and TMA dose first. But again, we can see a way to actually growing graphene and putting a gate material on top of it. And this is some work that's going on down at UCSB. They're looking at 2D transition metal using molybdisulfide and tungsten selenide, which is very promising for future resistors. So again, that's been reported in this paper here. And we can, if we wished, cluster a lot of tools together to actually make these chambers all quite separate. And so that makes it also scalable. So you can do research all the way through without breaking vacuum, which actually keeps the device surfaces and the interlayer surfaces very clean, no oxygen contamination. We've gone from small pieces. This is actually plasma graphene, which is only done 200 mil. but 100 mil as well. So if I summarize, we have deposited, and I've got capability of depositing CVD and ALD high quality materials. We can do 2D heterostructure fabrication. We've shown that, demonstrated that. We've also got the capability of etching these materials using ALE because they're very thin layers. And we also have the capability of adding in 2D layers of ALD material. I'm quite happy to take questions.
Apparently he's happy to be asked questions. Anybody working on 2D materials here? Don't all rush. Okay. Any interest in 2D materials?
I noticed in one of the process examples you showed, you had it was a tungsten oxide.
Yes, and then you can.
Hydrogen sulfide.
Yeah.
Does that heat the same structure? The graphic kind of implies it, but
I'm not a 2D materials expert. I don't know if Mike knows, but I think it does give you the same structure. I think it just replaces the ox.
I'm not sure that's known yet. I mean, I think a lot of these conversion works have been based on stoichiometry and element analysis, and backing it up with Raman or XRD is more patchy. But it seems to be a promising way to go.
But again, you've got to go higher temperatures again to do that anneal. So that recent result on the 2D materials from on the Flexile, it was done at about 300 degrees C. So again, it just makes it a lot more compatible with CMOS type processing and other materials. And if that carries on that way, and we get other materials we can deposit that way, I think that will be looks like a very promising route to it. It's also very controllable. It'll be very uniform as well.
What's the maximum height to width aspect ratio can be for your ALD deposition?
Oh, aspect ratio? I don't know if we've ever looked at.
For example, you have a given height, for example, 100 nanometers, and how we have two of this 100 nanometer height close. What's the minimum gap it can be? Right. Given you have 100 nanometers height, how close can it be?
ALD can get into smaller structures than you can etch. People use ALD to infiltrate porous materials. So ALD is extraordinarily penetrating. Usually the problem is to fabricate the high aspect ratio structure, not to coat it with ALD.
It's very, very dependent on also, if you've got a time dependency, I would say thermal you can get up to about 100 to 1, but if they're very small pores, then you have to probably dose for a very long period of time to actually make sure your material gets into that, then purge it out. So it will very much depend on your aspect ratio, but 100 to 1 is not unknown for thermal. For plasma, I think 50 or 40 to 1. 20, well, fair enough, 20. I knew it was lower than thermal. For plasma, for thermal, then it's about 100 to 1. Easily. Yeah.
So which means there can be 1 nanometer scan with 100 nanometer height.
There is somewhere in one of our presentations with the porous openings of very, very narrow gaps, coating down to 100 to 1.
As long as the atoms fit down the gap, I think that's the trick. And of course, you've got a transport limitation. How long will it take for gas to go in and out through a long, narrow pipe? It'll take a long time, so you've got to extend your cycle time, which is what.
It won't be the same cycle time as if it was this wide and that deep. If it's that deep and that wide, then you're obviously going to have to change the cycle time to actually make the gas. It's a transport effect.
Maybe next time I show SEM or extremely large.
But this is about doing 2D materials. It wasn't doing about ALD.
Well,
we quite have to come back and do an ALD presentation.
If we've got SEMs of ALD coatings of AAO templates, anodic aluminium oxidation templates, and those are extraordinarily small, deep pores, and we've done coatings in those. So, you know, I challenge you to find something that thermal ALD can't coat.
As long as you want to wait long enough.
Yeah. Last question, anybody? Okay, thank you, Rob.
Thank you.
So, do we have Ryan Briggs here? We do.